Hello everyone, welcome back to the next lecture for Geography 101. Today we're going to be talking all about erosion and the movement of sediment and rock through a landscape. So the erosional process is all included within the concept of denudation. So denudation is the overall processes that dictate the disintegration and transport of rock. So that includes weathering, mass wasting, and erosion, which we'll go over in more detail throughout this lecture. So weathering is the physical or chemical disintegration of rock. So if you have a parent rock of bedrock, weathering alters that rock and breaks it up so that it forms smaller fragments and regolith. And the process of doing that is known as weathering. And it tends to be accelerated at the surface where that outcrop occurs on Earth, as well as deeper down along fractures and faults where water can seep in and cause weathering as well. The physical or chemical weathering tends to be determined which is more prevalent based off of the temperature and the amount of precipitation in an area. So an area that receives heavy precipitation as well as higher temperatures tends to have significantly more chemical weathering compared to physical weathering. And so chemical weathering is just the weathering process in which chemical reactions occur, whereas physical weathering is where some objects such as water or ice or wind, that's the material that's causing the weathering, and it's the physical action of that material that's breaking apart the rock. So first, let's go into chemical weathering. So chemical weathering is the disintegration of rock through chemical reactions. And you can see an example of a rock that's been heavily chemically weathered. And so there's a number of different processes that fall within chemical weathering. The first of which is oxidation. And this is just when oxygen bonds with ions within a rock. For example, iron. So iron and oxygen combine to make Fe2O3, which is hematite, which is one of the major components that cause rocks to have a reddish hue to them. And sometimes they have a incredibly dark red hue as the iron content of that rock increases. The next process is hydrolysis. So silicate minerals can absorb water slowly over time, and that water gets actually incorporated into the chemical structure of that mineral, and it can form clay minerals instead. For example, the most common example of this is feldspar that experiences hydrolysis and gets converted into kaolinite, which is a type of clay mineral. And you can see that here in the chemical formula as well. You have feldspar that has water added to it, and as a result, that chemical formula now has that water incorporated into it. And you can see the result of that here with the darker colored kaolinite. Here's what these different minerals look like alone. And kaolinite tends to be a more friable and easily erodible material. And here's what it looks like under the microscope. It's much more platy than the feldspar tends to be. The next type of chemical weathering is carbonate dissolution, which we've talked about a lot previously. This is the process of carbonate minerals that can dissolve. For example, carbonates within the shells of organisms, when they get exposed to acids such as carbonic acid, they dissolve away. And so the more carbon dioxide that the ocean absorbs, the more carbonic acid that's formed, and therefore the more dissolution that occurs with that calcium carbonate eroding away and not being able to be used by these organisms that make their shells. You can see that too here. This is a statue that was made from calcite, and it was exposed to acid rain, and it's now dissolving away. This also occurs within soils. So soils can also have a low pH, high acidity. Generally, soils that have a lot of rainforests and a lot of productivity tend to have fairly low pHs. You can see here the Amazon rainforest and Southeast Asia tend to have very low pH soils. And so this carbonate dissolution can happen underground as well and further weather the rock. Additionally, we have salt dissolution. We all know that if we poured salt into water, then it's going to dissolve. And so salt is a mineral just like any other. And so when it gets exposed to rainfall, it can dissolve away as well. So a lot of times you have very large geologic deposits with heavy amounts of salt in them. And as it gets more and more exposed to water, that whole rock surface will more easily weather. Most of that salt forms either in a dried lake bed, and as salt and the minerals dissolves away, it can get washed into a dry lake bed like this and form these large geologic regions like this one. Next, we're going to talk about physical weathering. So physical weathering is any process in which some material is causing the breakup of rock by the movement of that material. And so the most significant one usually is frost wedging, especially in cold climates. So frost wedging is when you have water that seeps into a crack in a rock, and then it freezes. And so as it freezes, ice expands. Ice is less dense than water, so it expands when it freezes. And as it does, it expands by 9% because of the density difference of water and ice. And then it produces about 2,000 pounds of pressure. And so that's a significant amount of PSI in order to kind of pry this rock apart. So frost wedging is a major component of weathering. Next, we have frost heaving. It's what has caused this road to be so bumpy. And it's a process that occurs in cold regions as well. So what happens is that water layers can develop in the soil, and as the temperature drops, then these water layers freeze, and the soil above them gets heaved upwards as that ice takes up more volume. And so you can have that process kind of breaking up the rock as a result. Additionally, it doesn't have to be ice that's causing these cracks to enlarge. You can also have salt wedging. So usually rain has a small amount of salt or minerals dissolved into them, and as that rain gets into cracks and evaporates, then that salt is left behind and starts to crystallize. And as those crystals grow, they push out on the rock and can provide pressure to physically weather that rock and expand the crack. You can see that happening here, where the salt has entered the cracks and is starting to break it apart, as well as here as well. Another type of physical weathering is thermal expansion. Whenever you have an area that has significant changes in temperature throughout the day, such as desert regions that are very hot during the daytime but fairly cold at night, a rock can expand in response to that temperature change. While you may think of things expanding and contrasting more so for like gases or some other material, rocks do so as well, just to a much smaller degree. And when you have big temperature changes, that that expansion and contraction over and over again can cause stresses to build up and fractures that eventually lead to weathering and exfoliation of that material. We can see that here in this graph, that this is the expansion of different types of rocks based off of their temperature. And now most life on Earth happens right in this region, and so that rock is only expanding by maybe 0.1%, but over the course of that entire rock, and because it's happening every day nearly continuously, that stress can start to build up and those micro fractures start to get worse and worse. Another process of physical weathering is exfoliation. So this is when kind of entire sheets of rock material pop off in layers from a large uniform rock surface. And this is really common in places with plutons. These are the intrusive igneous rocks that we talked about previously. And so this happens because that pluton formed when it was under immense pressure. So it was deep underground. And so in order to maintain its structure, it had to have an outwards pressure. But as that material is eroded away and no longer supplies pressure to that rock, then that outward pressure now exerts a force on the rock, and it can cause blocks of rock to pop off, or as we call it, exfoliate. And sometimes this happens fairly slowly, but also it can happen fairly quickly. You can see here, this is a layer of rock that has been exfoliated off and leaves behind this new lower layer. You can see here that it can also sometimes be somewhat explosive, in which the fracture kind of propagates quickly within the rock and it just kind of bursts off. Another major physical weathering force is biology. Organisms can erode rock as well. You can see here a tree root that's growing into a crack in a rock. That's known as root wedging, and trees can provide significant amounts of pressure to fracture and weather a rock. As the tree root grows, it can push against the rock with 1,500 pounds per square inch. So it's not an insignificant amount of pressure that the rock is being exposed to as this tree grows. Additionally, lichen and microbes can grow on a rock, and they can act on the individual grains in that rock and scour it away, as well as adorable little creatures such as gophers that burrow into the rock and scratch away at it. Additionally, as you have more burrowing occurring, you have water more easily infiltrating into the soil, and that exacerbates weathering as well. Burrowing does not only happen above land. You have a lot of burrows in the ocean as well. These are eels in the deep ocean. And so they can burrow into the soil, and sometimes those burrows get left behind within the rock record, and we call the remnants of their burrows bioturbation when we see that in the fossil record. So once you have rock that has been weathered and is formed into smaller components, it has to get down the slope. So the process of rock moving down its original slope is called mass wasting. And so that movement down the slope happens due to gravity. And it can happen in a number of different ways based off of how much moisture is in the soil. And that can, we tend to classify these different events based off of how much moisture there is, as well as how fast the process is. And we'll go over these different processes from slow to fast. So one of the slowest processes is soil flocculation. Sorry, that's always a hard word for me. Also known as jellification. So this is when you have water that seeps into the soil and kind of turns it into a jelly that slowly slumps down and forms these lobes. And so this is a fairly slow process with a moderate amount of water that just kind of causes the slope to not have as much integrity. Next, we have soil creep. So this is similar, except it tends to form occur when there's less water. So soil can act somewhat like a viscous fluid, and so it will slowly flow downhill. And you can see evidence of that in these micro topography here, as well as these tilted signposts that have been tilted as the soil creeps downhill. And so, yeah, that's soil creep. Next, we have slumping or rotational landslides. And this occurs when you have fairly consolidated material that breaks free from its parent material and rotates as it slides downhill. And it will form these different blocks here. And we can see evidence of this here in these rotational slides, where this block of material originally started here or here, and then it slid downhill and rotated as it did so. So we have a number of different terms to describe the different aspects of the slide. The main important ones are the scarp face, which is the steep face in the parent material that's left behind after the block has moved down. The top part of that block is called the head, and the bottom part is called the foot, and the edge being the toe. So an entire slumping occurs along this rupture surface, and then it moves down in multiple blocks downhill. Next, we can have landslides or translational slides. So this occurs when you have a fairly cohesive layer that can't deform the layer below it. It's a fairly cohesive layer below it. And so instead of rotating, it'll just slide down along this rupture surface. And so pretty straightforward. It's moving along this surface from this upper region down to this lower region. And we can see an example of this here when all this rock that was up in this location here just gets translated down into this region where it's now covering the road. Next, we have rock falls. So this is a picture of the Palisades in northeast New Jersey. Beautiful hiking spot. And you have rocks that have fallen off of this cliff face and have just fallen down into the river here. And so one of the most dramatic rock falls occur in Yosemite Valley, and we'll hear about that now.
In the particular rock fall that was captured on video, you can see a rock slab detaching from the cliff face, sort of skipping down the cliff face, hitting a prominent ledge, breaking up into a bunch of pieces. And some of those individual pieces are 40, 50 feet on a side. And those pieces then are free falling through the air, spinning on their way down. They fall several hundred feet, and then they impact the talus slope at the bottom. And some of those huge boulders will be moving down the talus slope at 40, 50 miles an hour, snapping large trees like matchsticks and going all the way down to the base of the talus slope and the valley floor.
We're standing at the base of the rock fall that happened on August 26th of last year, 2009. And this is one of the rocks that fell from it. I thought they were about that big, you know, because we were about, I don't know, half mile away. So they didn't seem that big. But now looking at it, they're huge. It's amazing to think that it came down from up there and then bounced. I guess it must have bounced, right?
And prior to August of 2009, this slope had large oak trees on it. But when several thousand tons of rock came down off the cliff and landed in this area and then moved down the talus slope, those boulders basically wiped out all of the trees that were on this slope. And this talus slope leads right down to the floor of Yosemite Valley, and just beyond the edge of the talus slope is the Iwani Hotel. If these rock falls were occurring in a remote valley, they would be of scientific interest only. But because these rock falls are occurring in Yosemite Valley, a narrow valley with nearly 4 million visitors a year, they are more than a spectacular natural process. Depending on where and when a rock fall occurs, it can have potentially serious consequences.
Yeah, so that's rock falls. They can be a very serious event. Next, another type of mass wasting that's not often thought about are avalanches. So snow and ice is a mineral just like any other. And so when it moves downhill, then it's a mass wasting event just like any other as well. So there's two different types of avalanches. There's slab avalanches, in which an entire block of material slides downhill. And there's point avalanches, in which there's a point disturbance, usually in loose snow compared to the more compact snow for slab avalanches. And that point literally snowballs into a larger avalanche and triggers more and more snow to fall down. You can see an example of a slab avalanche here, and the entire block gets moved downhill as a continuous unit. And this usually happens when you have fresh snowfall over a layer that's weaker and has been exposed to the sun for a longer period of time. And then when you have a large windstorm that blows and provides weight on this slope, then the whole thing can trigger and move downhill. Here are some examples of point avalanches where you have this one point and it's kind of carved out an avalanche path down the slope and taken out all the trees that have fallen below it. So the top of an avalanche, the escarpment that forms there, is known as the crown, whereas the bottom of the block where the avalanche came from is called the Stotch Wall. And so it eventually flows downhill and reaches the toe of the avalanche, and it gets deposited. Another dramatic type of mass wasting is debris flows. And debris flows are pretty much lahars that we talked about previously that aren't associated with a volcanic event. So instead, they're triggered by just torrential rainfall. And we'll see some examples of debris flows now. Yeah, so debris flows are definitely serious, and they can move truly massive boulders downhill, just because there's so much water there that it's causing the sediment to just get completely swept away and formed a slurry that's moving down. And that slurry can move boulders much more easily than water could alone.
Pesca las puntas, cava leña, luz. Tipo pesca rendida.
E sente il tiro entre mani.
Ves che sa scardina. Devo che va a cambiare rapidi.
Cioè, fai un video perché
Yeah, so mud flows are definitely serious business. So we're going to continue on talking about erosion, which is the transport of rock and sediment from one location to the other. But first, we're going to take a short break, and we'll come back to talk about erosion. All right, see you guys soon.